Welcome to the SAFI UAE webinar series. Thank you for attending. We are in our second session. This series is an 8-part series. We had our first session last week. Today's session is titled Pathways to Produce Sustainable Aviation Fuel, or SAF. We have with us three very distinguished panelists. My name is Alejandro Rios. I am the director of the Sustainable Bioenergy Research Consortium at Khalifa University of Science and Technology. And first, to begin with, I would like to thank our sponsors, our co-sponsors, the Boeing Company, Etihad Airways, the General Civil Aviation Authority in the UAE, and IATA. With that, I would like to introduce our speakers. As mentioned, we have three very distinguished speakers. First, we have Mark Rumizan. Mark has been the Federal Aviation Administration's regulatory and technical expert for aviation fuels for over 2 decades. He has been employed by the FAA since 1991 and is currently the Senior Technical Specialist for Aviation Fuels in the Aviation Certification Division. He is also a member of the Commercial Aviation Alternative Fuels Initiative, CAAFI, Steering Committee, and is the leader of the CAAFI Certification and Qualification Panel. He serves on the Executive Subcommittee of the ASTM International Aviation Fuels Subcommittee and is the chairman of that subcommittee's Emerging Fuels section. We then have Dr. Jennifer Holmgren. Dr. Jennifer Holmgren is the CEO of the revolutionary carbon recycling company, LanzaTech. Prior to LanzaTech, Jennifer was VP and General Manager of the Renewable Energy and Chemicals Business Unit at UOP LLC, a Honeywell company. Under her management, UOP technology became instrumental in producing nearly all the initial fuels used by commercial airlines and the military for testing and certification of alternative aviation fuel. Today, under Jennifer's guidance, LanzaTech is working towards deploying carbon capture and reuse facilities globally to make fuels and chemicals from waste carbon. In 2015, Jennifer and her team at LanzaTech were awarded the U.S. Environmental Protection Agency Presidential Green Chemistry Award, and she received the Bio-Rosalind Franklin Award for Leadership in Industrial Biotechnology and the Outstanding Leader Award in Corporate Social Innovation from YMCA Metropolitan Chicago. She was named Most Influential Leader in the Bioeconomy by Biofuels Digest in 2017 and received the Digest Global Bioenergy Leadership Award in 2018. A member of the National Academy of Engineering, a dog lover and committed greyhound rescuer, Jennifer holds a Bachelor of Science degree from Harvey Mudd College, a PhD from the University of Illinois at Urbana-Champaign, and an MBA from the University of Chicago. Jennifer is also the director and chair of the LanzaJet Board of Directors. LanzaJet Incorporated is a new company that will produce sustainable aviation fuel for a sector requiring climate-friendly fuel options. And finally, we have Dr. Bruno Miller. Bruno is Managing Director of Fuels and Regulatory Affairs at Fulcrum Bioenergy, a pioneer in the development of a reliable and efficient process for transforming everyday household garbage into low-carbon transportation fuels, including jet fuel and diesel. He is responsible for directing Fulcrum's fuels activities, including sales, logistics, regulatory compliance, and sustainability. Dr. Miller has more than 20 years of experience in the air transportation industry. As a strategic sourcing manager in the fuel department at Northwest and Delta Airlines, he was responsible for the airline's fuel supply chain in the US Northeast, Latin America, and Africa, including major airports in New York, Boston, and Washington, D.C. As principal of energy and environmental at Metron Aviation, he analyzed and developed strategies to strengthen the leadership of major global airlines on sustainability and environmental performance. Dr. Miller has been principal investigator in a number of projects for the National Academy of Sciences Airport Cooperative Research Program and was the co-chairman of the business team of the Commercial Aviation Alternative Fuels Initiative. He holds a PhD in air transportation systems, as well as a Master of Science and Bachelor of Science in Aeronautics and Astronautics, and a Master of Science in Technology and Policy from the Massachusetts Institute of Technology. So with that, I would like to give the floor to Mark, who will start us off with his presentation. So Mark, please go ahead.
Thank you, Alejandro, and good morning, good afternoon, and good evening, everybody. Again, thank you, Alejandro, and good morning, good afternoon, and good evening. I'm going to spend the next few minutes speaking about how we evaluate and approve alternative jet fuels or sustainable aviation fuels for use on our aircraft and engines. And just two quick points at the start of the presentation. First is that despite the fact that this is organized around ASTM International, this is a global process. The approvals follow the aircraft, and the aircraft fly globally, are purchased and are used by airlines all over the world. So it is a global process. Secondly, this does not address the emissions, environmental impact, or the sustainability of these fuels. It is exclusively focused on the safety and the performance of these fuels. So how do we qualify a sustainable aviation fuel for use? First, we in aviation consider fuels as operating limitations. They're approved with the aircraft and with the engines. And the fuel that's virtually approved on virtually all aircraft and engines worldwide is Jet A or Jet A1 fuel. And again, virtually all aircraft worldwide are approved to operate on fuels made to the ASTM Jet A or Jet A1 fuel specification. Next, we have a process to evaluate any new candidate SAF or alternative jet fuel to compare it to fuel made from petroleum, conventional jet fuel. This process, the criteria, the testing that we use for this process are defined in an ASTM standard D4054. So after that evaluation is completed, if the sustainable aviation fuel does meet the conventional jet fuel specification and properties, then we add the new sustainable aviation fuel to our drop-in fuel spec, which is another ASTM standard, D7566. Each new sustainable aviation fuel or alternative jet fuel is added as a new annex to this specification. And currently, all of these fuels, the annex defines testing properties specifically for the new sustainable aviation fuel. And after it's tested, it is then blended with conventional jet fuel. And the blending percentages are between 10% and up to 50% right now. And that may increase with the future as we get more experience. And it is a drop-in fuel after blending, but not before blending. Next, because the drop-in fuel spec is a more stringent version of the conventional jet fuel spec, all fuels...
Mark, sorry to interrupt, apologies, but I believe we can't see your screen. Your screen is not moving. So maybe you can, I don't know if you need to click on the presentation mode, but we can't, we're only seeing the initial screen of your presentation.
You're only seeing the title slide?
Correct.
Oh, I'm sorry. Hold on a second. You, are you
There it is. There it is. Yes.
slide 2? Okay, I'm sorry. Okay, let's, so as I was speaking, I went through really the first 4 steps. I'll go over them quickly. The first step in the concept we use to approve alternative jet fuels is based on the fact that fuels are approved as operating limitations. Operating limitations are based on ASTM specifications, and these are global approvals that are tied to the aircraft. The second step is our evaluation process, which is an ASTM standard D4054. And that evaluation process is set up to compare the alternative jet fuel to conventional jet fuel. And if the alternative jet fuel or sustainable aviation fuel meets all the properties that a conventional jet fuel does, we add it to our drop-in fuel spec as an annex. And the sustainable aviation fuels are blended with conventional jet fuel at percentages between 10 and 50%. And after they're blended, then it is considered a drop-in fuel. And because the fuels and the drop-in fuel spec also meet the conventional jet fuel spec, this brings you full circle around to the fact that now these fuels meet the existing operating limitations. So because they meet the existing operating limitations, they're acceptable to use on the aircraft and engines. So effectively what that means is that once you are added to the ASTM drop-in fuel specification, you have approval to fly. The significance of this is that there is no separate or subsequent step required to get an approval from the airworthiness authorities or the regulatory agencies. Because this process provides evidence and proves that the new fuel is the same as existing fuels, so therefore it's safe to use. So no additional approvals are required. It's very significant that there is no additional FAA approval or EASA approval or any other regulatory agency. So over the last, it's really a decade and a half, since 2006, when we started CAFI, the Commercial Aviation Alternative Fuels Initiative. When we started CAFI, one of the biggest concerns or one of the biggest risks or perceived risk at that time was regulatory agency approval. And because we developed the process that I just showed on the previous slide, we've been able to march ahead and make a lot of progress over the last decade and a half. We issued our drop-in fuel spec, D7566, in 2009. When we issued that specification, the first annex for the first alternative jet fuel or sustainable aviation fuel, depending how it's made, Fischer-Tropsch, was included in that annex back in 2009. Later that year, we issued our alternative jet fuel evaluation process. And then we've progressed down this road and subsequently approved 7 annexes. As you can see, every year or two, we end up approving a new fuel. Most recently, or in 2018, we added ethanol to Annex A5, and Jennifer Holmgren will talk about that. LanzaTech led that effort. And then more recently, in December 2019, we approved CHJ fuel, which was developed by a company called ARA. The significance of that fuel is that it's a fully formulated jet fuel, and technically it doesn't need to be blended, but it still has a 50% blending limit because we want to get experience with it before we extend that limit. And then most recently, and this past May, we approved hydrocarbon HEFA. And just again to emphasize that this is a global process. The company that led this effort, IHI, is a Japanese company. So it is truly a global effort. And so you can see we've made a lot of progress over the last decade and a half. Let me continue. Let's take a closer look at the evaluation process itself, because that's the key to this whole process. That's the biggest hurdle to getting through it. Because these new fuels have to work on the existing engines, it was a requirement of the engine aircraft manufacturers that these fuels, the new fuels, had to be drop-in fuels, because it is basically impractical to try to redesign the existing fleet of aircraft out in service, because there are so many out there, and they've been produced over decades. So there's tens of thousands of aircraft out there. So the philosophy was that we would develop drop-in fuels. The ASTM D4054 evaluation process is structured to determine if the new sustainable aviation fuel is in fact the same as the existing conventional jet A fuel and is therefore a drop-in fuel. The first part of the process involves an evaluation of the fuel properties. Tier 1 are the specification properties. These are the properties that you see in the fuel specs. For example, D1655, the conventional jet fuel spec. But in addition to that, we have additional properties that we test in tier 2. These are fit for purpose, tier 2, these are fit for purpose properties. And the tests are much more extensive, get into a lot of properties that you wouldn't normally check on fuels. That then completes phase 1, where we have a report that's issued, and there's an initial review by the engine and aircraft manufacturers, what we call the OEMs. As part of that review, recommendations are made by the OEMs for what the extent of, or what type or the extent of tier 3 and tier 4 testing, which is where you get into testing the fuel on rigs, test rigs, for example, combustor rigs or fuel nozzle rigs, and also possibly testing the fuel on complete engines or auxiliary power units, APUs. Upon completion of that testing, there's a final report issued. There's a final review by the engine aircraft manufacturers and the FAA. And only after this rigorous and extensive process is completed, which can take several years, only after all that's completed, then is a new annex proposed to the ASTM membership, where it's balloted and added to the drop-in fuel specification after the balloting. So the reason we set it up this way is that obviously the safety and performance of the fuel on the existing engine and aircraft is critical. So that's why we go through those initial reviews with the engine and aircraft manufacturers. The balloting to the ASTM membership is to make sure that we didn't miss anything, because the fuel also has to be compatible with the distribution infrastructure, the ground refueling systems, and other comments we might get regarding producibility and other aspects of the fuel. So the ASTM membership balloting typically produces a lot of good feedback. So this is the same process. The format's a little different here, but it is the same process. As I mentioned before, we've had 7 annexes issued that have gone through this complete process. And several of them took several years, up to 9 years in one case, so it can take a long time. More recently, we've been getting these approvals done in 1 year to 2 years. Working backwards along the chart, along this process, tier 3 and tier 4 testing, we have one fuel that is sort of in the middle of that, that's Virent, that's a purely aromatic fuel, blending, it's a blending component. Continuing to work backwards, a fuel that Shell is working on is currently being reviewed by the engine and aircraft OEMs and the FAA. And HFP HEFA, which is we also call green diesel. HFP stands for high freezing point HEFA. That is sort of stalled at that point, but it has stalled at that point in the process where the OEMs are still talking and reviewing it. Another version of alcohol to jet is being developed by a company called Swedish Biofuels. They're working on writing their report right now. And then finally, we have a new entrant, Global Bioenergies. I mentioned before we had one company from Japan that was just approved, Global Bioenergies from Europe. And they have just started their testing. And in addition, we have several companies that are speaking to the ASTM community about starting the evaluation process. We consider these exploratory discussions. They really haven't started testing yet. One company is about ready to start testing, and it's called, the name of the company is Vertimass. So you can see this is a continuing pipeline of these candidate fuels. Some of them do drop out. It is a very rigorous process. As I said, it can take several years. It can cost a lot of money, but it has to be rigorous because our primary concern is the safety of use on aircraft and aircraft engines, which is very, very critical. And I mentioned when I went over the process on the second slide, that the basis for allowing the use of these fuels is that they've been found to meet the existing aviation fuel operating limitations of the existing fleet of aircraft. To communicate that, the FAA has issued a bulletin, which we update with each new approval of each new annex. This bulletin is available from faa.gov. You can also contact me and I can send it to you. But the intent of the bulletin is to communicate that these new fuels are the same as petroleum-derived jet fuel. They should be handled in exactly the same manner. There's no special requirements or criteria, and that they're approved for use on existing aircraft. So as I said, you can get this bulletin from me if you need a copy, or from the FAA website. So thank you for listening. I'm going to remain available for any questions, and I appreciate your time. Thank you.
Thank you very much, Mark, for an excellent presentation. I think you laid out the fuel approval process very clearly, and even though it's a difficult process to understand, and I'm sure that many people will have questions, you have done a great job explaining it, of course. I want to remind the attendees that you can post questions in the Q&A box, and we will make our best effort to get to all of your questions at the end of the presentations. With that, I would like to turn now to Jennifer and ask her to put up her slides and go ahead. Thank you, Jennifer.
Thank you so much, Alejandro. It is a great pleasure to be here with all of you, and I really appreciate the invitation. Let's start by telling you at least our view on carbon. If you think about our need to reduce carbon emissions significantly, and if we think of ourselves as being on a carbon budget, then what that says is that we should only put carbon where we need it. I would say the levelized cost of electricity today using solar and wind is equivalent to that in most locations of natural gas or coal. And so that means that energy is getting to the point where it can be substantially carbon free. However, aviation fuel and chemicals are going to need carbon for a very long time. And therefore, to put ourselves on a budget, we want to reuse carbon whenever possible and put it where it is most needed. What we do is we recycle carbon emissions. So we have a bacteria that ferments waste gases. So carbon monoxide, hydrogen, and carbon dioxide from an industrial site are compressed into a bioreactor. It's a continuous bioreactor, and our bacteria eats that and makes ethanol. The ethanol, of course, can be used in automobiles, but the ethanol can also be converted thermocatalytically to jet fuel or converted via ethylene to packaging and other products. We have also learned how to modify the microbe to make chemicals directly from those gases. And so that allows you to use the same equipment to make different products. If you think about the technology, carbon monoxide, hydrogen, and carbon dioxide are not only available at industrial sites, but they can also be made through gasification of municipal solid waste or biomass, or someday you can imagine taking CO2 from an emission source, and when electricity is green, the electrons will be cheap, right? And so what that allows you to do is to use electrolysis, either coupled directly from that CO2 flue gas or directly captured from the air, and then through electrolysis, the CO2 converted to CO, carbon monoxide, which can then be fermented with the exact same platform. This last bucket is called often power to X, because you're essentially using power to convert CO2 to X being fuels and chemicals. And so it's an exciting trajectory, and one which, to be honest, I think is going to become important in places like the UAE, where in fact solar can be such a big player. This all sounds a little bit like science fiction, but it's not. We built a commercially operating plant in China. It is running outside of Beijing at a steel mill, taking carbon monoxide, only carbon monoxide. There is no hydrogen in the stream, and the bacteria converts that to ethanol. It makes its own hydrogen via water gas shift. We have prevented in that period over 70,000 tons of CO2 from being emitted in the air, as this carbon monoxide would just go up the flue normally. The economics of this process at the China site make quite a bit of sense, and the project will pay back in under 5 years, closer to 3 years. The economics of this process very much depend on the gas value, because carbon monoxide can be used for power, and you have to pay for it, even if it's a waste stream, and also the value of the ethanol. In many jurisdictions, ethanol is subsidized, and so the combination of the gas price and the ethanol price will make the economics make sense. This map shows you at the top right, it says 60 million liter per year steel off gas. That is the plant whose picture I've shown you. The steel company is called Shougang. In addition, because they are so happy with that operating plant, they have partnered with a ferroalloy producer who also has similar gases, and they should have an additional plant running in China at the beginning of next year. We're also building a plant with ArcelorMittal at their steel mill in Ghent. That plant should be operating in the second half of next year, and we're using a refinery off gas in India. So
It seems that we are losing Jennifer. Jennifer, can you hear us? Okay, it seems as if we lost Jennifer. Unfortunately, her internet connection might have skipped for some reason. So what I will do is ask. Hopefully, she can log back in, and as soon as she does, we can go back and. Okay,
Sorry,
no, here you are.
sorry.
It's okay.
When did I lose you?
So you were talking about the ArcelorMittal and then the refinery off gas in India.
Okay. Oh my gosh, I'm so sorry.
No,
Um,
please, please. Go.
so what I was saying is those plants will be up and running in the second half of next year, but that shows you the diversity of the feedstock sources, refining plants, ferroalloy and steel gas plants. We have a gasified municipal solid waste plant that's been operating. That's just a pilot unit, very small. It's a demo scale using gasified municipal solid waste. And the other two projects I show here, the Ametis and the Swayana project, they're just in the raising the financing stage. So I don't have a date when they'll be up and running. But if you look at all of these gases, accessing all of these carbon wastes, we can imagine making over 2 trillion liters of ethanol. And that is a lot of ethanol. And so the question becomes, we don't actually need that much ethanol. Um, However, my view is that um, ethanol can become a substrate for making other products. If you can make enough ethanol from these feedstocks that you cannot aggregate, like municipal solid waste or waste gas, you can convert those to jet fuel, which we have done, and also to other products. The process to convert alcohol to hydrocarbons, jet and diesel, is a thermocatalytic, not a biological process, which was first developed by Pacific Northwest National Lab in collaboration with the Department of Energy. And what we have done is we have scaled that process to make large samples. The work was all certified under RSB. Mark has already talked about the ASTM process, and I don't want to do that, but I do want to make a comment. Do not underestimate how much work Mark does to help all of us get certified. It's really an extensive process, as you saw. After we were qualified under ASTM for commercial flight, we were able to use some of this fuel to fly from Orlando to Gatwick on a Virgin Atlantic commercial flight. And more recently, we've been working with NRC to look at the overall sustainability impact of this aviation fuel. In order to commercialize the technology and to accelerate that, we partnered with Mitsui, Suncor, and ANA, as well as the Department of Energy, and we are now very far along in building a 10 million gallon per year, that's almost 40 million liters per year of aviation fuel. That will be a demo, and it will be up and running probably in December of next year, 2021. Now, what we did with this cash raise is the investors agreed that if the demo looked good, they would commit to building 30 million gallon a year plants. So they committed the cash already for that construction. As soon as they see the KPIs, they can move forward. The reason we did the cash raise this way is because normally when you're trying to scale technology, between the demo and the first commercial, you spend a lot of time proving the technology, but also raising the financing. So this allows us to go more quickly. Here I show the sustainability profile, including the greenhouse gases and the water impact. At the end of the day, the key is for the jet fuel, for the SAF emissions, is the ethanol feedstock source. So what you're seeing, the lower the ethanol life cycle, the lower the ATJ SAF product. Now in the MSW case, you can go even lower, as well as in the biomass, because sometimes you can also include avoided emissions. If an MSW site is decomposing and emitting methane, you can actually take credit by converting that MSW for avoided emissions. I did not include avoided emissions in any of these calculations. It's very site specific. I would also say that these type of synthetic fuels make great blending components. Because they don't have aromatics, they can uplift the properties of conventional petroleum kerosene. They don't have sulfur, they have a higher energy density. And as our work with NRC Canada has shown, they also have lower contrail and particulate emissions. In my mind, the reason that alcohol to jet is such a potentially important technology is we're not the only ones making ethanol. A lot of other people are making ethanol through different approaches, and so the feedstock becomes a regional source, and therefore the feedstock is plentiful. And so what you can imagine is distributed production of ethanol followed by a centralized conversion of that ethanol to aviation fuel. You could, of course, keep it in a distributed fashion and just integrate the ethanol and the jet production, but you could also imagine hub and spoke model. We have to do something about carbon, and often we wait a little bit too long, and we're waiting for magical solutions, and that's not going to save us here. And so for all of you in government, I would ask that you consider a few things that will make the production of new fuels go faster, because at the end of the day, what we need to do is scale much more quickly. So to conclude, I would say that one of the things we're trying to do is really put carbon in the circular economy and do that at the basic carbon level. Today, a steel mill makes steel, but the off gases are often wasted or underutilized. We can capture that and make fuels for cars or planes, and we have shown that we can do that. We can also make products like the seat belts that are going to go on those planes using recycled carbon emissions, and someday we'll be able to do even more than that, including acetone acrylics, MMA, PP, polypropylene, etc. So using circular carbon principles is, I believe, a path to reducing our global carbon emissions. Thank you very much.
Thank you, Jennifer. Thank you very much for your excellent presentation. I think it very clearly lays out what LanzaTech is doing, but it also opens a number of questions that are very interesting for this region of the world. Because this part of the world does not have many of the sources that other regions of the world have in terms of the capacity to produce ethanol. But we'll get to that set of questions a little bit later on. I would now like to turn the microphone over to Bruno so that he can give us his presentation. Thank you, Bruno.
Thank you, Alejandro. And thank you again for the opportunity to be here. It's a great honor to be able to be participating in this webinar alongside with Mark and Jennifer and yourself, all true leaders in the space. And today I wanted to give you a little presentation about the Fulcrum Bioenergies. We are a municipal solid waste to fuels company. I wanted to share some of the story and the plans that we have. So the company got started about 10 years ago with the fundamental premise of trying to solve two big global problems. On the one hand is the problem of what to do with the waste, municipal solid waste, which in many parts of the world ends up in landfills, in a hole in the ground. And on the other hand is the need to decarbonize transportation, and aviation in particular and freight transportation are two really hard to decarbonize sectors. So the idea behind Fulcrum was to look at the resources, all the carbon-rich material that is being wasted literally in landfills, and try to come up with a way to turn it into fuel to decarbonize aviation and other transportation modes. I'll go in a little bit more detail as to our process. But so the route we take, we produce a low carbon fuel. Like Jennifer suggested earlier, municipal solid waste is a good feedstock, is carbon rich. And it also solves the problem of methane emissions at landfills. This is a drop-in fuel. We use the Fischer-Tropsch process. It was coincidentally the first annex that was approved under 7566 that Mark told us about. So this fuel has been approved for many years. Because of our feedstock, which is a waste, the economics look very, very beneficial, and we are able to produce a product that is competitive with current jet fuels. And the whole integration of the technologies has been patented, which creates also a solid basis for commercialization of the fuel. No, we're not doing this alone. This has been a long road so far, about 10 years, working alongside with many partners. So our view of the process is to look for partners along the entire supply chain. We have waste partners, including Waste Connections and Waste Management. These are two large waste companies in the United States. We have 20-year agreements for the feedstock with these companies anywhere in the country. We also have partnerships with technology companies such as Abengoa and Marubeni, and also partnerships with oil companies like BP, Marathon, and World Fuels, which they've looked at our process, at the business model, and they've decided to become investors. And same with end customers, a number of airlines, United Airlines, Cathay Pacific, Japan Airlines, that are interested in the low carbon fuel and have also become investors in the company. In terms of our process, we are doing essentially a three-step process. We begin with the waste. We do a sorting of the waste, and I'll show a few more slides on that. And then we do a thermochemical process where we gasify that waste and turn it into jet fuel with the Fischer-Tropsch process. Here is a picture of our feedstock processing facility. This is in Reno, Nevada. As you can see, it's very dry. It's very desert-like. And this facility is located within the boundaries of a big landfill. You can just kind of see here on the top right corner, that's where the landfill is. So we're literally the last stop for this waste before it goes into a hole in the ground. We have an agreement with the landfill. We have a series of lights. So if we turn the light green, then the trucks come into our facility to dump the waste. And this is what happens. So the waste gets dumped on our floor. This is the tip floor, because this is where the garbage trucks tip the waste. It's a very creative name. And from here, we introduce it into sets of machines. These machines are very common in the waste recycling industry. We didn't invent any of this. We just arranged it in perhaps a different, in a different way. Because what we're doing here is we're getting rid of the stuff we do not want in our feedstock. As you can see, or as you saw, this is the waste coming straight to the landfill. So it has a lot of unwanted material, a lot of metal, aluminum cans, bottles, metal pieces of chairs or furniture that we remove using magnets. We also remove the very wet waste. And we also get rid of inert material like dirt, rocks, that kind of thing that we don't want in our gasifier. At the end of this process, we shred the material, the organic material, and it creates this type of confetti. This fluff is very dry, which we like for the gasification process. It's very low in inert material, including metals and rocks and dirt and glass. That's all has been removed, or it exists in a very minimal quantities. And this is the material that then will be brought to the biorefinery. This is a picture of the biorefinery. It's a few miles away from the feedstock processing facility. As you can see, it's still under construction, but we are projecting finishing construction here in the next few months and have it operational at the end of this year. Here in the foreground, you can see these are the feedstock conveyor belts. There's a feedstock building. The feedstock is then moved into the gasification island, which is here in the foreground. This is where the feedstock, the organic material, gets gasified. It's essentially decomposed into gases. We clean up that gas and then create what is called a synthesis gas. And that synthesis gas then goes through a Fischer-Tropsch reactor. And out of the Fischer-Tropsch reactor comes the hydrocarbon liquid that we can then turn into either jet fuel or diesel or other products to be marketed. And this process, so we're using municipal solid waste because it's abundant and we have these agreements with the waste companies. But we've also demonstrated the process with woody biomass. You can also use agricultural residues. And so to echo, say, Jennifer's comment about multiple feedstocks are available in different parts of the world, this platform can also be used the same way that Jennifer was alluding to process different types of feedstocks. So we also envision a way where different locations, we have different solutions, but they can use the same technology platform to do that. And with that, I'd like to thank you for your attention. Thank you.
Thank you very much, Bruno. I think that is a very clear way of presenting what Fulcrum is doing. And it opens the door for a number of questions that are related to how we can approach the idea of producing sustainable aviation fuels in this region of the world. As you know, we are a water-constrained region. There really is very little to no biomass to speak of. And so we have a number of constraints that are not present in many places around the world. And I wanted to bring your cases to bear here, because in the examples that you have very clearly presented, one is the case of fermentation of gases in the case of LanzaTech. And then the other one is this process for using Fischer-Tropsch technology and converting a syngas into a liquid hydrocarbon fuel. Before we get into the specifics of that, I wanted to ask Mark, what would you consider to be the biggest barriers in the fuel approval process? I mean, obviously you mentioned cost, you mentioned, the time it takes, and Jennifer said, that you do a lot of heavy lifting to make sure that the process moves forward. But what, in your experience, what are the major barriers and blocks that you think are most relevant in the fuel approval process?
Well, we've made a lot of process improvements over the last decade, and we've learned a lot. Ironically, I think the biggest challenge we faced is the difficulty that the candidate fuel producers have to be able to make sufficient quantities of fuels to support the testing. So we really haven't been paced by the inability to run tests. We've been really paced, again, by the supply of the test fuel. But again, we have made a lot of process improvements. We now have something called a fast track provision, which allows fuels that are let's say, they're less unique. They look much, their properties are very, very, let's say, nominal relative to conventional jet fuel. IHI used the fast track process, and we were able to get them approved in a year, making perhaps 100 gallons of fuel. So we do have, and then just one other thing I want to mention in terms of challenges relative to approval. We right now, even after a decade and a half of working on this, we don't have any large scale production of these fuels. And what we're waiting for is large scale production to gain experience in producing and using the fuels. When we do that, we'll be able to make more improvements into the process, because we'll understand the risks, if there are any, or we'll confirm that we've been doing a good job, and we can back off on how stringent we are in our testing.
Understood. Thank you. Moving along, a couple of times we've mentioned this, and Jennifer mentioned it very clearly, this idea of this P2X or P2X concept, right? Which essentially is the idea of taking off gases and, in a sense, doing what part of the process that Bruno has mentioned, which is to capture these gases through a CCU system, and then combining them with a low cost or low carbon, more specifically, energy source, so that you can do electrolysis and then perhaps create this syngas, and from the syngas to produce fuel. There have been a number of examples. Specifically, if we look at the feedstocks that are available in this region of the world, we have, of course, municipal solid waste. We have very little, but some agricultural waste. But we do have off gases, right? We do have heavy industries. Oil and gas is a major industry here. There's been a lot of talk about lower carbon aviation fuels. But what I'd like to ask you is, how do you see this power to liquids, or these electrofuels coming online? What are for example, in the fuel approval process, as far as I understand, these fuels are approved because even though they come from waste gases, the methodologies or the technology to turn them into a liquid hydrocarbon fuel has already been approved. So maybe each of you can chime in, because again, garbage is a major source here, and off gases are a major source here. And so I want the people in the UAE to understand what it takes to reach the production of these fuels. And perhaps Mark, you can tell us about the fuel, and then either Jennifer or Bruno can chime in.
Yes, Alejandro, as you stated, the Fischer-Tropsch pathway is approved, and the definition of the pathway starts with syngas. So anything upstream of the delivery of the syngas is acceptable, whatever means is used to produce the syngas. So the quick answer is that it's approved, and you don't need me anymore, so you can move on to Jennifer and Bruno and ask them their opinion, but it's approved.
Thank you. Perfect. Go ahead, Bruno, please. Or yeah. Jennifer, go.
No, Bruno, go.
Yeah. Well, we will always need Mark, so don't listen to him. But you're right, we're approved, so that's good. I think I want to stress on the feedstock, and especially for the economics. Alejandro, like you said, the municipal solid waste, obviously it's a waste. The off gases can be considered under certain circumstances as a waste. That's important because building these new facilities takes capital, and you are competing for that capital with other projects. So your economics have to be very, very solid. And starting with a very low cost feedstock is a great way to do that. Once your facility is up and running, then you can go to more expensive feedstocks. But to begin with, in order to make an economic compelling case, looking at waste feedstocks is important.
Thank you.
I would just add that, you know, I believe that power to X, or whatever we want to call it, is going to be increasingly important. The grid is getting green really, really fast, and the marginal cost of an electron will become very, very low. So using it for energy intensive approaches like electrolysis is going to be very, very doable. And we'll be able to make ethanol from the CO2. And I think actually it's a very exciting opportunity. The only comment I would make is we cannot wait for that day to happen. We need to create solutions and start implementing them now. My biggest fear is that direct air capture plus power to X becomes kind of the holy grail, and people just do nothing until the time when those technologies make sense and are viable. So that would be my only comment in addition to what's already been said.
Okay, thank you. I have a specific question. I mean, there's questions in the Q&A box that relate to specifically to the technology that LanzaTech is using. And there are some questions in terms of the risks and the contamination of the fuels that have been raised. However, I would like to address, so I've been talking to people here in the region, and many, not many, but a couple of projects, large-scale projects that are using municipal solid waste have preferred to go via the incineration route. And so I wanted you guys to give me your sense of, I mean, clearly, and you know, the people here have very explicitly said, you know, the problem we have is that we haven't been able to get a gasification project financed. The people lending the money are not familiar with the technology. They don't seem to see any projects of this nature around the world, and therefore they are not willing to finance these projects. And that is why we're going through the incineration route. And so can you please give me a sense of, you know, what is being left on the table in a way when we incinerate versus trying to reuse this carbon and trying to produce something of value?
Do you want to start, Bruno?
Yeah, go ahead, Jennifer.
Go ahead. Yeah. So I would say, look, I don't think it's just technology risk in terms of using MSW to make ethanol, jet fuel, whatever route, right? There's technology risk, which is what the financing people are telling you because of the fact that there aren't commercially operating plants doing that today. We have a pilot running that has been running for 4 years, so we know that it works, but I can understand people saying the commercial one isn't running. But what I would also say is overall incineration versus gasification plus some type of conversion process is more expensive, right? On a unit of feedstock to unit of product, the dollar of capital investment. But I would also say that the higher value product will pay back. It's just a question of getting there, right? Of actually investing in the capital. The other thing I would tell you is, if we really want to reduce carbon, I believe, and my partners in Japan who have the MSW plant believe, that MSW is the oil field of the future. We have so much carbon locked in municipal solid waste that we could really make huge volumes of product. We have to start thinking about using that carbon right, which is not for power production. But certainly I understand the decision to go with incineration first. Bruno?
Yes, it's like Jennifer said, to a big extent it's a matter of what is available commercially today. Incineration is well understood. The facilities are cheaper to build. But you know, so we've faced this hurdle, and we've been able to raise the capital to build our first plant, which should be completed very soon. So that will be a good demonstration that the technology works, and hopefully that will spur more investment. In terms of incineration, there is a concern about the emissions that come out of the stack. Gasification is closed loop, so you capture all of the pollutants and you can dispose of them safely. So you see incineration that it's also, there tends to be community opposition when an incinerator is going to be built nearby, and that's one of the main concerns. So gasification could be another way to be able to cite where an incinerator would not be possible for policy and political reasons.
Okay, thank you. Being mindful of the time, we're already, upon the hour here. I would just like to, very quickly from each of you, what is your view on the future of sustainable aviation fuels? How do you see the industry moving, and what is your outlook on the future of SAF? Perhaps Mark, you can go first.
Sure. Yeah, as I mentioned earlier, we're continuing to work to improve the fuel evaluation and approval process. So hopefully we'll make it easier for new candidates with new technologies as they arrive and propose their new fuels. Obviously, I don't want to comment on the economics of it, but obviously government support is a huge element of this, and that's very important. But again, we'll continue to work on improving the process, and we'll make sure any fuel we approve is safe to use on the airplanes that all of us fly on.
Thank you, Mark. Bruno?
Yes, I think there's going to be multiple solutions according to what your local strengths are. I think the UAE has many resources, like Jennifer suggested, and you too, Alejandro. There's a lot of sun. You have a strong refinery complex. So as long as you produce you can do the first few steps, and then you know that you can put that product into your refinery complex. And so, yeah, so look for your strengths. We need all of the solutions. There is not a single solution for everybody. And the more diversity we bring to the table, I think the better will we be.
Thank you, Bruno. And last but not least, Jennifer?
Well, I would echo everything Mark and Bruno have said, and just add one minor comment, and that is we are at a perfect time to really grow the SAF business. I'm seeing a lot of interest. I'm seeing a lot of the COVID recovery be focused on greening the economy and finding new ways to do things. So I think this is a beautiful time for SAF. And I'm really excited about the possibility to implement this technology in the UAE and everywhere else.
Well, with that, I would like to thank our panelists. Thank you very much, all of you. Thank you for your support. We will be posting both the presentations and the session recording to our website. And don't forget that we will have a weekly session of the SAFI UAE webinar series, for the next 8 to 10 weeks. Again, thank you to our panelists, and thank you all for attending. I give it over to the control room to close the session. Thank you.
Thank you.